Bismillahirrahmanirrahim. Greetings. The lecture in this video is intended to be a preface for a first course in calculus. Now, calculus, whether single or multivariable calculus, differential or integral calculus, completely sits on the concept of limit. Formal and rigorous mathematical definition of limit, known as delta epsilon definition of limit, will be given later in this course, and I intend to put 2 or 3 video tapes only for that topic. High school mathematics is necessary and sufficient for this course, and it will be used mostly for algebraic manipulation. Now, in this video, I will not be attempting to make any formal definitions or attempt any kind of proof. Rather, I will be waving my hand and bypassing some of the terms and taking for granted that you are familiar with some of the terms. Now, there could be some kind of a little bit discrepancy and not exact, because this is a preface and I'm condensing the whole entire calculus into 50 minutes. So it will be expanded later on the entire course, and more precise the version of that definitely will come up. Now, in this video, I intend to use 2 kinds of geometry, regular Euclidean geometry, plane geometry, and analytical geometry, and both of them in a very elementary stage level. Now, I will be using these 2 geometries for 2 reasons. Number 1 is to improve your conceptual understanding about the subject, and number 2 is to use it as a visual aid to set up the analytical approach that can lead us to mathematical formula. I will be also using familiar examples to extract information that can lead us to the relation between the integral and differential calculus. Now, at the end, I intend to put a short talk about the history of the subject, and hopefully it will be beneficial for you. Now, behind this cardboard that you see, there is a whiteboard, but it was reflecting the light, the dry erase, and so I came with the idea of covering it up. I am using very primitive equipment, and I don't have somebody to step behind the camera to zoom in and out for me, so please bear with me, and until hopefully I will have a better equipment. Now, I can't think anything else about the introductory, but let's start, shall we? Now, suppose an object is moving with a constant velocity of, say, 2 meters per second. Now, with the word velocity goes direction, is implied, because velocity is a vector and the magnitude of that is a speed. Now, in other words, it means that the object is not just wandering around aimlessly or going around a circle, but has a specific direction it is covering. Now, since velocity is constant, therefore acceleration must be 0. And, and since velocity is involved, it's just common sense that distance is increasing. Now, let's put all of this in perspective, put it in geometry, and see what kind of information we can get out of it, and we can use it for other examples to come. So let's put this one into a picture. Now, here it is. My object is going with a constant velocity of 2 meters per second. Now, what is distance? Distance is velocity times time, length times width. Velocity is 2, we can call it height or length, and the time is t, you can call it width or length, either of them, doesn't matter. So here we can say distance equals to 2 times t, which is 2t. So therefore the area under this curve, under the graph of velocity, shows what to be distance. By the way, I call this one curve because the line is a member of the family of curves. So I can use a general name for the curve. Now, we want to know, now our interest is to find out what is the rate of increase of the distance with respect to time and see what kind of information we can get out of it. Okay, now let's go to the next handout. Now here, again, same thing, the area under my curve is 2 times t. Now I'm going from t, I'm fixing t. T is fixed, then I go to 1 second later, which is t plus 1, and see what is definitely the distance is increased. Now I want to see what is the rate of increase of that per unit time. Now here, I go as I have written here, hopefully it's visible for you. I say next one is 2 times t plus 1, and the previous one was 2t. So I do a very elementary arithmetic or algebra. I came up to subtracting the two areas from one another, the smaller from the bigger. We end up with 2 to 1. 2 unit increase of the distance per unit time. 2 to 1. 2 to 1. You see, I repeat that twice because I have a point about that. Now, I have a thing, a better, yes, I do. I have a better representation of that. Now what I'm going to do right now, I'm going to put, instead of going to 1, I'm going to go to half a second and see what is the rate of increase in that interval. Then I'm going to go to 1/4 and 1/8 and 1/16 and so on and so forth, so that you get the feeling. And each time I'm collecting data, I'm putting the data in the chart so that I can use it, I can see it organized way, so that I can see if I can come with some kind of pattern. So let's go and put the next one that I have written, so I don't have to go through the thing of that. Hopefully it's visible to you. My apology again that I don't have somebody behind the camera to zoom it in and out. Now here, from t fixed, I went first to t plus 1. We already talked about that. Now I go to t half a t. So it will be 2 times half a t minus 2t over what? Over half. That means 2t and 2t, they cancel each other, and 2 times half divided by half again end up to be the ratio of 2 to 1. Now next I'm going to see 2 to 1, I have written all this. Now next I'm going to go closer to the t that is fixed, and the interval of the time that I select will be 1/4 of a second. So that will be 2 times 1/4 plus 1/4, here is a 2 parentheses, t plus what, plus 1/4 minus 2t divided by 1/4. 2 times t and 2t, they cancel each other. 2 times 1/4 is 1/2, and 1/2 divided by 1/4 is again ratio of 2 to 1. So if I do that continue, 1/8, 1/16, 1/32, that I like you do it in pen and pencil, you will find that again the ratio end up to be 2 to 1, 2 to 1, 2 to 1. So then you ask question, hey, what's going on? Why is it 2 to 1 coming back? So when we put this one in analytical geometry that we are kind of more familiar with, we will see that the similarity of triangle is what is doing that, the ratio of 2 to 1. Now let me talk about it before I go and put it in the graph for you. Now here, distance equal to 2t. So d of t equals to 2t. And from high school mathematics, we know that the graph of d of t equals 2t is what? Is a straight line with a slope of 2. Since it is a straight line, every right triangle that we make, no matter how large or how small it is, the ratio, we are familiar, we call it rise over run. The ratio of distance over time remains as 2 to 1. That is what we got it in this figure. Now let me put it in the other one so that you may see what I'm talking about. And because the visualization I have written here of the phenomena is more appealing using analytical approach. Analytical geometry. Now here is the exactly same thing, is the distance, but the distance before we had was Euclidean geometry, the plane geometry were representing distance. Now analytical geometry is representing distance. And so you can say the previous one was a fat representation of distance, and this is a skinny representation of distance. Or you may say the previous one was two-dimensional representation of distance, and this is one-dimensional representation of distance. Now here, as you notice, the ratio of rise over run, I'm using the ratio and proportion, I'm going to talk about that shortly. Now here, the ratio of distance to time remains 2 because of similarity of triangle. Now here, as you notice, I have given now I'm dealing with what? With function, and function has input and output. So I give him t. By the way, now I go to the delta t instead of saying 1 and 1/2 and 1/4 and 1/8 and those that you left. I go to t. Then next one I say t plus delta t. And delta t is what? Is little change that I'm giving. I'm going to the right of t. So again, from t fixed, I go to the next point, which is t plus delta t. Now, what is delta t? Now, one good question you may ask is that why did you select why didn't you go to t1, t2, t3, t4, and so on and so forth instead of going to subject of delta t? Now, the answer is that if I go to t1 and t2 and t3 and t4 and so on, I'm selecting my points from a countable set. But when I go to delta t, then I'm selecting my point from uncountable set. And the other thing is that if I go t1, t2, t3, and so on and so forth, then I may end up with kind of mathematical induction, and I don't want to get involved with that. So I go to t plus delta t, and when I do that, when I'm 2 times t plus delta t minus 2t over what? Over t plus delta t minus t. So the denominator becomes what? The denominator becomes t and t. They cancel each other. So I'm left with what? I'm left with 2 times t plus delta t minus 2t over delta t. That when I simplify, I end up with what? I end up with 2 delta t over delta t. Now, before I continue, let me say a few words about ratio, about proportion and rate. Excuse me, I said proportion. About rate and ratio and what is the difference between them. And then talk about 3 words of mathematics that we live in. Now, ratio is comparison of 2 quantities with the same unit. Whereas rate is comparison of 2 quantities of different units. So again, I repeat myself, ratio and proportion, ratio and the rate, they are same. If we drop the unit for the rate, we end up to ratio. So rate is comparison of 2, both of them are comparison of 2 quantities, but the rate has a different unit. In a ratio, the units are same. Now, the other thing I would like to mention is that about the subject of delta t, to get the feeling. Now, I recall a few years back, maybe over 20 years ago, somebody, somebody in Japan, I don't know if that was a company or individual person was interested, he wrote a computer program for the digits of pi. And the amount of paper that he used, he went around the circumference of the Earth, of our planet Earth. Not I didn't mean he went around, but that amount of paper he used. Now look at that. This is one page. He writes 3.1415 da 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 da. Then he goes next line da 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 and so on until this page is exhausted. Then you go to the next page. You go to the next page, to the next page, and so on and so forth. How many papers he used? Now to seek for some kind of pattern. Of course, he didn't find out, and he couldn't also find what is the last digit in pi. Now, what is my point? 3.14 and da. Forget about the 3. Let's every digit of the pi, that many that guy has gone through, take each digit out and replace it with 0. And the last digit that he ended up, I don't know what it is, something from 0 to 9, put 1 in there. You see how small that number could ever be? Can you imagine of that? But that number is still a real number. Now then, what is infinitesimal? What is infinitesimal? Now let's talk about that one. World of mathematics lives in 3 different universes. The universe of infinity, that there are infinitely different kinds of infinity. The universe that we live, let's call it real world, and that is what we add addition, subtraction, multiplication, division, extraction of root, etc., etc., etc. we live in. And then comes the world, or the what will be the universe of what? Of infinitesimal, the midget universe, which is a universe of its own. But over there, I can say the inhabitants or whatever they live in that world are points. Now, then what is point? Point is dimensionless, does not have dimension. Now, what does it mean that you said a point doesn't have dimension? It means that it doesn't mean that it's empty set or doesn't exist. It does exist in the world of mathematics, but has no dimension. But infinitely many of them, they do get form and they do have dimension. Now let me make another example about that you can feel it better about the world of infinitesimal. Between the unit 0 and 1 and the entire number line, there is a one-to-one correspondence. What does that mean? What does that mean? There is one-to-one correspondence. This means for every point between 0 and 1 and points on the number line that already also includes 0 and 1, there is one-to-one correspondence. Now, this is not a magic or sorcery or fairy tale stories that I'm telling you, but this is reality, and mathematics proves that. And the proof of that is very elementary, it's kind of junior level, high school, and analytical proof we have for that also. So when we go to the world of points, a strange thing happen, and same is true when we go to the world of giant infinities. But that is, both of them, they are very interesting to go and study about them. But that is beside the subject. My point is that when you, between any 2 points, there are infinitely many other points. So when you stretch, the interval from 0 to 1, no matter how much you stretch it, the points immediately fill up the gap, fill up the gap, fill up the gap, so you go to the infinity. This is kind of, you can think about it. Now, when we go to the world of infinity, look what happens. Here we have 2 delta t over delta t. So you may think of as delta t approaches 0, the numerator approaches 0, denominator approaches 0, so therefore we end up with 0 over 0, which is what? Which is undefined. But that is not the case. Why is not the case? Because when we go to the world of infinitesimal, the ratio 2 to 1 remains same. You remember I said 2 to 1, 2 to 1 to 1, and we went here, and we said the slope of that no matter how small you make that triangle, this one, again the ratio of rise over run remains same. In the world of infinitesimal, you can say 2 pixels or 2 points to 1 point. So that remains same, and so it does not end up to the idea of that you think is 0 over 0. So and also the other thing, when we talk about limit later on, the limit of this is not limit of numerator over limit of denominator. That you say limit of numerator is 0, limit of denominator is 0, therefore we end up 0 over 0. Here it is. Pack up, let's go. That's it. Is some kind of paradox or contradiction or something came up. So hopefully you are clear here about the meaning of delta t and what it means when we say approaches zero. Okay, now let's go to the next handout, if you may. Now we finish with the excuse me, I have a running noise at this time. Now we finish with the first. Now we go to the next example. And as I said, the idea is what? To relate the area under the curve to the curve and see if there is any relation. So we finish with the first one and we end up that 2 to 1 stays same. Yes, there was a relation because 2 was what? Was our velocity, and the 1 was what? And the area under the curve end up to be 2 to 1. And 2 was the velocity, which means the one that area was under that. Now let's go to the next example. And the next example that we have, we go now with different velocity. Now, suppose our velocity now is no longer constant. It's under influence of acceleration, but we select first constant acceleration. Let's say 2. So velocity is changing, but the graph of the velocity will be linear. Now, this is the graph of the velocity. Now, the area under this graph from 0 to t, in the interval from 0 to t, t fixed, it will be, we are suspecting to be distance. Let's see if this is correct. So what is the area under this graph, under the graph of the velocity? Is 1/2 height times base. The height at t is 2t. 1/2 of 2t is t. T times base, which is t, t times t is t squared. So we suspect that the area under this, under the curve or the graph of the velocity is t squared. That is the distance. But immediately a critic will pick on us. He said, hey, not that fast, not that fast. You said the velocity is changing. So why in the world you selected 2t, which is the highest velocity in this graph? The velocity is changing. Who told you which one to select? And you said that 1/2 height times base. Height is 2t. Well, the critic has a point. We have to convince him, otherwise he prevents us defending our thesis and getting our PhD. So we have to convince him. How we can convince that? Fortunately, this graph is linear. And since it is linear, we can use the average, midpoint. So the average from 0 to 2t is t. So here it is t. So we can now assume that, and not assume, that is in fact a fact, that the object that is going with the velocity, constant velocity of t is fixed, in the interval from 0 to t, he covers the same distance from that the object that is going from 0 to t with change of velocity under influence of what? Acceleration, which is 2 in this case. Now, the guy who is going straight, he put the cruise on and he's singing a song that in the end of the tape, I may tell you what kind of song he was singing, but he covers the same distance. Now look at this one. This is a right triangle. This triangle, when I cut this one off and put it here, that if it is in class I may do it even as a demonstration with scissors, we want up a nice looking, what, a square. And if you want geometrically, and the plane geometry, you can prove that these two triangles are congruent. The proof of that is very elementary, I'm not going through that, so you can see it for yourself. So whatever is the area of this square is the same as area of both of this triangle. Since the area of the square is t squared, therefore the area of the triangle is t squared. Therefore we were right to say the area under that is t squared. So our critic now is quiet. We answered this question. Now let's go and see what we can come up with the next one. We go with the area under that and start again to see what is the rate of change of that area. Exactly what we did with the previous example. Now we are doing with the example that area is what is changing, is not, the velocity is not constant. So let's go to the next one if we may, shall we? Now, the area here, the first area is t times t is about t squared. The second area, we go 1 second later, we get t plus 1. So the area of the square will be t plus 1 times t plus 1. Now, if we subtract the area of the smaller square from the larger square, I have written here, we end up with 2t plus 1. Then question is, hey, where does 1 come from? Now, those of you who are a little bit familiar with the derivative, you know that the derivative of t squared should be 2t, then I end up with 2t plus 1. Where does 1 come from? Now, let's first put some number to see if it is correct or not. If this is t that I fixed it, let's say is 5, 5 squared is 25, then 5 plus 1 is 6, 6 squared is 36, 36 minus 25 is 11, which is 2 times 5 plus 1. So that is correct. So what went wrong? Nothing went wrong, but we selected the unit 1, which was terribly large in a sense. Now we are going to do exactly what we did before, to chop it down and chop it down and chop it down and get closer and closer to t. And each time that we do, we are going to collect those data, put it in the chart, organize it, and see if we can notice any kind of pattern. Now, I have written some of them here, so hopefully it's visible for you. So let's go now to the next one and see what we can come up with. By the way, this is this one I just said is a plane geometry representation of that. If we go to analytical geometry, we are kind of more familiar with that. So let's do that and see what we can come up with. Don't forget that the area is t squared. So what is the graph of t squared? We are familiar with that. So if we say d of t squared will be what? Will be the graph of a parabola. So let's graph that one and see what we can come up with. Now here is our parabola. Exactly what we did before. But here we go to t plus delta t. We know what delta t means. We are not going to 1 and chop it down. We take advantage. We go with delta t and we have upper we have, upper hand on delta t to chop it as much as we want. Now, this, since it is a function, so has input and output. So we give the input as t plus delta t, he gives us t plus delta t quantity squared. We give it t, he gives us delta t squared divided by this interval. This interval is t plus delta t minus t, which is delta t. So I have written here. Now, here, when we clear that one, algebra, very elementary algebra, very elementary arithmetic, we end up with 2t plus delta t. But for most of the books, most of the authors, they start here from limit, which is really definition of derivative. They start from limit because what? Because they want to show that is what? That is rate, that is ratio. So we are taking under consideration that this delta t, even though they cancel, we are still what making comparison to the change of time. It's not that delta t when we cancel it disappears the time. So the comparison went away. It's still there. So when you go to that, now what I do here when I reach this level, I take limit at this time after I explained it, of course. When delta t approaches 0, what happens? Gradually, eventually, goes out of our world, goes to the universe of what? Universe of the midgets, universe of the points. When you reach that, then it's out of our world. So we end up with 2t as the answer. So we know now what was 1 there and how 1 went away from us. Now, let's see what we can come up now with the next one. The next one that we make, again, our critic will pick on us. He said, hey man, don't go too fast. All the examples that you selected for us so far was what? Was the one that plane geometry was easy to calculate. It was regular polygon. Was started with a rectangle, then a square, then a triangle. What about if the area under the curve end up to be what? End up to be something that plane geometry was handicapped to give it to us. There was no formula. And he has a point, we have to answer it. So how we do it, we go to the next one, and that is where the integral calculus takes over. So let's see what happens in that case. Now, this example we finished, don't forget that. Now we go to the example that we say this graph is looking same, and purposely I did that. Again, it's parabola I selected purposely. No, this is velocity now. This is the graph of velocity. Previously was distance. Now this is the graph of velocity, and the area under that we suspect from the three examples we made to be what? To be distance. But we have to show it because our critic is taking, and he's very well educated himself. He wants to pick up and see if we can answer his questions. Now, to answer that question and show that yes, this is what? This is indeed the area. What do? We have to find the area under this curve and show yes, excuse me, I said area. This is indeed distance. So what do we do with this? We are handicapped. We don't have the formula that we had. So what we do, we go, this integral calculus, in fact, was known to man we have evidence, for 5,000-6,000 years before Christ. The ancient Greeks, they were using that, and they call it exhausting technique. And what they do, common sense, the caveman could do it. We don't even have to go to medieval time. And that is, we fill up the area under the curve with rectangles. And we start to make this as rectangles skinnier and skinnier. And by doing that, what we end up with, we fill it up. If we fill the area under with this kind of rectangles, if you notice this rectangle has this much less than a trapezoid that you can see that fills up is corresponding into under the curve. So this has this much less. If we fill it up with this kind of rectangles, the area of them, when we add them together, will be less than what? The actual area under the curve. On the other hand, if we fill it up with this kind of rectangle, which we take the right end point, then we see that this rectangle has this much more. So when we add and add and add, the area that we get is a little bit more than the actual area under the curve. So area under the curve will be sandwiched between these two, squeezed between these two, and then we can see, because we are collecting data, we notice what kind of number is approaching. Now, I go to the summation notation to make it a little bit more clear for you, this subject. Now, here, summation notation, I have limited time, I have to rush before the time is over. Now, here, this summation notation is that, let's just make an example. Let's say from 0 to 10. With the 0 to 10, 1, 2, 3, 4, 5, the rectangles that we make, the width is 1, each of them, and the height, we give it to this function, he gives us what? He gives us height. In the previous example, we give it to x squared or t squared, he gives us height. We have the height, we multiply by the base, we get the area of the rectangle. Then we add it to the next, and so on and so forth. Now, then we increase the number of rectangles. Let's say we go half a unit, whatever unit we selected. Now we have 20 rectangles to get area. And then, so n becomes 20, and we give left end point, right end point, which means we go area a little bit more than the area under the curve, and area a little bit less than that when we add those area of those rectangles, and we start to notice what's going on, the chart that we are selecting. Now, here we go to 10, from 10 we go to 20, then we go to 100, which means we divide each unit into 1/10, so 100 of them will be from 0 to 10, and we add them all together. Now, the addition, the benefit of this notation, alligator notation I call it, looks like alligator, summation notation, is that it condense what? The summation. Otherwise, we have to write plus, 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 you may go 1 mile paper. So here it condensed that, and with the condense also what? Also comprehension increase. So there is a lot of advantage for that. Now, this one, the art of topology can come and then push this one inside and push this one from inside this way and end up to be the sum. And now, this sum, so what I wrote here, the connection between antiderivative and summation comes, that was Leibniz and Newton, there was a big dispute, but I give the credit to Leibniz. We talk about it at the end of the lecture. And this, now the advantage of that is that now integral calculus give us precisely what is the area under that curve without going through rectangles, adding together. But the idea starts from this. From primitive idea starts before he discovers something more kind of advanced. Now here, the thing is that the derivative, which is the rate of this is this without the upper and lower bound, this is a function in its own right. Now the derivative of this function, the derivative of this snake is equal to what is inside the stomach of the snake, which is f of x. Of course, there is a c coming out. I call it m and m candy, but that is something that when we take the course and go, we will see them, the family of that. We cannot cover everything in one lecture. Now, let's go to X-rays, and hopefully we are done with this. Now, this is the X-ray showing the bone, showing all the bones here. Now, look what happens here. This is the graph of velocity. The graph of velocity in this case is the derivative. And this is the area under that curve, under the velocity curve. And this is the two-dimensional representation. And this parabola is what? Is one-dimensional representation of that. So both of them represent area. We have gone over that. Now, this one, if somebody says what is the rate of increase of this area under the curve at x equal to x1, you give this x1 to the function of the derivative, and the function of derivative gives you output. Always is a number. The output that he gives is the rate that this one is increasing at that point. The very same is true when we go with the one-dimensional representation. The only difference is that at one-dimensional representation, we go to the point on the graph. That is what the rate we are talking about. So let me say it in word before I go through that one. I'm not hopefully over the time. Whenever you take the derivative of a differentiable function, you always obtain another function. The value, function has input and output. The value, the output of the derivative function at any given point x will be what? Will be the rate that that function increasing at that point. At that point. What is point on the graph? Point in a 2D has x coordinate, y coordinate. So is x and y coordinate at that is where the rate we are talking about. Now let's say it another way, is that whenever you take the derivative of a differentiable function, you always obtain another function. All right? The value, the outcome of that function, which is always a real number, is the slope of the tangent line to the graph, which is order pair, to the graph of the original function, the mother function, at that given point. So that is the X-ray. Now this is not in a scale. I have another one which is more in a scale. I was trying to be precise with that one. So let me put that one for you, and hopefully it is visible. I'm sorry I don't have the option of zooming in and out for you. I don't have anybody to assist me, and I'm a skin. I have no other family member. Okay, now here is look at this one. The area again exactly same as before. The area is x squared. If I give him, let's make example. If I give him 3, he give me what? He give me what is the rate of the increase of the area under the curve at x equals to 3. You give 3 to the derivative function, he gives you 6. So the rate of increase of the area under the velocity curve at 3 is 6. Now if you give it to the one-dimensional form of that, to the parabola, to the analytical geometric representation of that, we give 3, he gives us 3.9. At this point, at 3.9, when you say what is the rate of change, then you go and put 3 to the function of derivative, he gives you 6. Then you say the slope of a tangent line at 3.9 is what? Is 6. The rate of change at that point is what? Is 6. Now I have 2-3 more minutes let's go quickly and finish the geometry, the history that I mentioned. Now the history is that Leibniz should be really credited for discovery of this fundamental theorem of calculus because he published it. Now Newton claimed that he knew that, but he had the proof because he has published it. And there was a big dispute between these two contemporary physicists and mathematicians, and was very hard, in fact, and it continued for almost 100 years. It is kind of childish to say that they were fighting for arguing for that. And to the level that they accused Leibniz of stealing the idea from Newton, which is very absurd. But anyhow, now the last thing I would like to mention is that, let me see everything I've said here, yes. No, is that I'm responding to the ask for a possible teaching position, and inshallah I may get one. Then I will try to use the facilities of that institution for much better quality of videos, and I intend to put more videos in calculus and other freshman, sophomore level mathematics. And if you live by any chance around Wichita, Kansas, and you could possibly assist me for zooming in and out and camera, and you have some skill with computer for software for editing, please do contact me. 316-371-6976. And the last thing that I would like to mention is that curiosity killed the cat. But in science and mathematics, curiosity makes what? Makes Einstein, Leibniz, Gauss, Euler, and Muhammad Ali the greatest. And I and Muhammad Ali, we have two things in common. And the second one is that we share the same name. And what else? Nothing else I think comes to my mind. So what I will say, have a great prosperous life, and until next video, I wish you a prosperous and happy time. So long. Oh wait, I forgot. I knew I forgot one thing. I promised you that I tell you what song our friend was singing. He was singing in the rain. Is it singing in the rain or dancing in the rain? One of the two, maybe both of them. But anyhow, his voice was 1,000 times worse than mine, so you're very fortunate you didn't hear him singing. So that was just a little bit joke in the end. I hope that could put some kind of smile on your face, and inshallah that smile stays on your face as long as you're on the surface of the earth. So long until next time. I'm saying so long so many times, am I not? So long. Singing in the rain.